Good afternoon, or rather good evening to everyone. I'm actually going to be talking about compilers. And so without sort of getting you really excited, this is a 20-minute talk, and we're talking about compilers. So we're not going to get through a lot of stuff, but at least I'll give you an, you could say, a gist of what has been happening in the Rust ecosystem as it relates to compilers, and why we are thinking about compilers as well. So yeah, the title of the talk is Compilers in Rust, and Cranelift is a project, and we'll talk about it. So just something about me. I work for Bosch, that's obvious, and I've pretty much written a lot of Rust code, many different open source projects. You can look me up on GitHub. And I lead a team of Rust experts, where we focus on things like high assurance software development, cryptography, basically stuff that nobody likes, but somebody has to work on them, so we'll take the job. And then I also want to give you some disclaimers. So this particular presentation is going to focus on compilers and their increasing significance. I'm pretty sure all of you heard of the word AI. Should have heard of the word AI. Pretty much, the world of AI is actually possible today because a lot of what's happening in the compiler space. You may have heard of things like, TensorFlow or PyTorch or JAX or any of these frameworks, which are all built on top of some sort of compiler abstractions. We'll get to that, if we have some time. But effectively speaking, you could say the main meat of things that you get to normally see, that is people writing frameworks or software or any other piece of code, it's no longer about the software. It's mostly about trying to write the best possible piece of code for your domain. And in order to do those things, that is your domain and the best possible experience for your domain, you really need to get into a space where you need to be able to talk to the machine at the lowest possible level. And that's where compilers come into the picture. So the other thing is, I'm also not affiliated with the Cranelift project. That's another disclaimer. But we're very interested in it. We will hopefully be much more closely working with the Cranelift team. I didn't do that.
Yeah.
Okay. All right, so in 20 minutes, we're not going to cover a lot of depth, but if this talk actually excites you, the goal of this talk actually is, there's a lot of YouTube streams that I do in my free time. You can actually watch them. I dive a little deep into whatever I'm learning about, specifically about Cranelift. So there's that. Just in case, if you think that I've left you hanging, there is a way to get more information about this. So what's the agenda? We're going to look at what a compiler really looks like. Just a show of hands, has anybody worked in compilers? Somewhat, yeah.
Not much, but like...
You can use just hit them.
Not much, but as a test compiler, was just compiling simple C programs in college.
Oh, cool. So it's I would say it's actually a double-edged sword, I'd say. It's interesting, and also it's very boring when you get to some parts of it. But when you get to the interesting parts, I'd actually like to focus on the interesting parts today, so that you can get excited about it. There's also something called LLVM. Anybody heard of it? Yes? Okay, cool. So we're not going to talk about LLVM. You just don't like it. Just saying. But I'll tell you why LLVM may not be the right fit always. It's not that LLVM is bad. LLVM just may not be the right fit for many scenarios, and we'll talk about that. And then we'll get into the meat, which is what is Cranelift and what makes it really cool. Obviously, it's written in Rust. That's partly why it's cool. That's what I think. And then specifically, why am I even talking about compilers and compiler engineering? I'll give you some example use cases as it relates to the automotive domain as well. and then maybe if time permits, we'll actually look at, if we can look at a demo, we can just try and look at that. Alright, so to get started, so if you were to look at a modern compiler today, you'll have three things in there at a very high level. You'll have the front end, you'll have what's called the mid end, and then you'll have what's called the back end. The front end is where you all will love working with the compiler. You keep getting all your error messages and stuff, and this type doesn't check out. There's a borrowing issue over here. There's an ownership issue over here. All of that stuff. It's happening in the front end. All right. In the middle end, you're doing a lot of optimization. What kind of optimization? So to give you an example, there's a particular optimization called common sub-expression elimination. It's very simple if you actually think about it. If you take x plus y is one expression, and if you have multiple places where that x plus y is defined, you could probably replace it with just one invocation and not keep computing x plus y in many different places. So that's the mid end. It's an example of that. You can have optimizations over there. And the back end is essentially what takes whatever comes out of the mid end and produces actual machine code. The code that runs on your device for a particular target architecture is what the back end does. And this first design was actually pioneered, or rather, it was pioneered by LLVM. And the person who actually pretty much wrote LLVM is Chris Lappin. He's also somebody who's, apart from writing, creating LLVM, he's also gone on to work for Apple and build the Swift programming language, and a whole bunch of other things. Right now he's working on Mojo. I don't know if you've heard of Mojo. Yeah? Alright, so obviously a compiler engineer built a compiler backend. He's going to use his compiler to effectively write more programming languages. So that's essentially what happens. If you look at the front end, you take C, C++, Go, Rust, Toy. By the way, Go LLVM is not the official front end for Go. I just put it there because there's another project. You basically take all of this stuff. The front end takes your source code and converts it into what is called an intermediate representation. In the compiler world, intermediate representations are pretty much what you will see. That means your source code keeps getting converted into multiple different forms along the way, till it gets to the machine code form. Right? The reason we do this is because you can't really reason about code at a high level. Example, in your source code form, you want to do all of this stuff. You really want, certain kinds of optimization done at certain stages of what is called the compilation pipeline. So you get the IR, you pass it into the optimizer. Optimizer produces some optimized IR, and then that goes to the backend code generator. The code generator is going to generate some code, right? And that's what comes out as machine code for your respective microarchitecture, which can be x86, ARM, RISC-V, whatever it is, right? This is what a modern compiler looks like, and the key word that I would use over here is it's modular. So, anybody heard of GCC? I'll get to the part, but yeah, right? Everybody should have heard of it, especially if we're in the automotive world, should have heard of that. Well, GCC was the original compiler toolchain that pretty much every language, legacy language that you can think of, uses it, even today. It's used by a large number of projects, the Linux kernel included. Obviously, there are some reasons for that. But GCC was mostly considered a monolithic piece of code. Just, then it didn't really have these, clear-cut modular design. It was a single piece of code where you could pretty much, take some source code, compile it, you'll get your machine code up. It was very difficult to, start a new, you want to write a new language, or you want to add a new backend. Stuff tends to get very difficult, right? So the first thing that I see where innovation really was needed was this kind of a design, where compiler is no longer just one monolithic block of code; it's modular at this point. And I'll give you some examples of what compilers look like. So this is stuff that if you are working in the open source, and you're working with any of these open source languages, Rust, Swift, Haskell people over here. So there's pretty much the front end, the mid end, and the back end. And if you look very closely, you'll see that pretty much every modern language today is powered by LLVM. Right? That's what. So although GCC has been around, GCC was around much longer than LLVM because it was the first compiler, I'd say, or compiler framework. But you'd see that pretty much every new language just uses LLVM. And that's, partly because of its modular design as such. GCC, of course, has multiple languages. I would call them, no C or C++ fans in the room, right? So yeah, legacy languages, to say, except for biology. So. All right, so this is what an open source compiler would look like. Now, since we're also sort of talking about compilers, let's also look at what closed source compilers look like. This is stuff that we don't get to see. We usually have to sign a contract, pay some money, get the tools and the tool chain to compile this code. So each player over here is an actual tool chain provider. They sell their products. And some of you may have heard of them, some of you may not have heard of them. But these are very specifically in the safety domain. Green Hill, Staffing, High Tech, all of these players. All right. Even in this case, you will see, if you see the bottom High Tech, it's actually a compiler that's based on LLVM. The rest of the other guys built their own stuff because they were around much earlier. But you can see the significance of LLVM everywhere, right? It's been there for a while, and the design really took off. The community is really invested in it. There's a lot of development that's been happening over the last 20 years around LLVM. But there are some drawbacks, or there are some areas where LLVM just does not cut it. And the areas are the LLVM code base itself. If today you wanted to say, okay, you're inspired by what you just heard, saying LLVMs everywhere, and you went to actually start learning LLVM, the total code base that includes everything is about 20 million lines of code. All right, just to give you some context, the compiler is 20 million lines of code, and it has a massive code base along with a lot of complexity already baked into it. Even today, for a beginner to get started, at least in our opinion, it's very, very difficult, right? So, things that are problems with that are, debugging is a real pain. If you're pretty new, you need to get up and running. You need a certain level of comfort with it. Generally, this is underestimated because we think that this is stuff that you can learn. This is stuff you can pick up. The amount of time it takes for you to actually get really well versed with it is pretty long. By many, if you go read about a lot of blogs, you'll see that that is the case. The wrap-up time is pretty long for that. Secondly, today you will see, I will show you in a couple of other slides as well, where it's no longer the CPU that we're compiling code for, where we're running, let's say, software on the CPU. We're running software in multiple different places, the GPUs, accelerators, digital signal processors. They're not CPUs per se. They're not your traditional general purpose processing code. You have specialized codes that are coming into being because we have specialized workloads, and a lot of the workload is shifting. LLVM has historically not been known to be very effective in that scenario, and I'll tell you why as well. Some examples are NVIDIA. It has an LLVM backend, but it's not exactly used. It developed its own what you'd call intermediate representation called PTX. Google's TPUs effectively use MLIR, which is another implementation in between. So that's not really efficient over there. Then there's also at least this is not true, the third point, which is performance cost, is not true everywhere, but it's certainly true in the embedded space. The amount of abstraction that LLVM has, I only talked to you about one IR. Actually, I was lying. There can be multiple intermediate representations when you're dealing with something like LLVM. That is to go from source code all the way to machine code you're not just looking at one intermediate representation, you'll be looking at multiple ones of them, and that can really get complicated as we get into the embedded space, considering the domain we're operating. Again, limited domain support. This is sort of tying into the third point. We don't use LLVM for very specific things like digital signal processing, etc. There are some use cases you can always use them, but not fully. So these are the areas why we would not use LLVM. So then the question pops up, what can we use? Well, so Cranelift is a project by the Rust community itself. It's a fully open source project. You can go ahead and hack it as much as you want. It's completely open source. It doesn't have like a very restrictive license as such, very much like what LLVM offers. Again, like LLVM, it's focused on 4 different things. So unlike LLVM, it's focused on 4 different things. It's focused on simplicity. The core code base, I mean, including all the comments and stuff, is only 200,000 lines of code. That's 200 versus 20 million lines of code, right? That's a massive difference, right there. And then the first goal of Cranelift was it was actually invented and it was actually designed as a backend for the WebAssembly runtime, a very specific one called WASM time. Anybody heard of WebAssembly? Yeah. So WebAssembly is an up-and-coming format. It's pretty much what people want to use in the cloud, at the edge, in your device as well, and that's exactly why we're talking about it. It's also something that we want to use in embedded devices as well. The goal of Cranelift was to actually support that use case, but now it's actually a little more than that. So I'll let you in on a little secret. Cranelift is the only other compiler backend that Rust supports officially for its debug builds. That means if you were to compile Rust today and you were to switch to the debug build, you can actually use Cranelift rather than LLVM, which is the standard backend that is currently used to compile Rust. So you can actually use, right now, you can experiment with it. That's what the demo was that I was going to talk to you about, but anyway, we'll see. So there are inherent benefits. Number one is simplicity itself, faster compilation, and also Cranelift is sort of taking a lot of pain and ensuring that they make the best possible compiler as it pertains to correctness of that compiler, using all of the abstractions possible with Rust. We'll get to the Rust part, but also they are investing a lot more in ensuring that whatever code the compiler produces is rock solid. It's possibly proven to be correct as well in some cases, and that's also a stated goal of Cranelift. So that's great. Now this is a Rust conference, so we need to talk about Rust. The thing that Cranelift does, the thing that gives Cranelift all these 4 things, which is faster compilation, simplicity, etc., is in large part due to Rust, because Rust has the necessary ingredients, as Johan mentioned in his talk, to produce high quality, reliable, safe, performant code. And you can actually write any kind of systems code. Compiler is systems code. You can actually write a compiler in Rust itself. And obviously, all of the benefits that were mentioned by Johan, again, apply to the compiler space as well. I'll give you some examples of them, because again, I didn't want to get into the whole details in just 20 minutes. But memory safety and thread safety, that's concurrency safety, are given. You can take it and do a lot with it. But beyond this, there's a lot of stuff that we can do. For example, we can go ahead and use the Rust type system to actually create a very, very good abstraction for Cranelift that will allow you to say, first off, the compiler itself is not going to be like, 100 MB or 200 MB when you sort of compile it and install it in a system. It's going to be very small, it's going to be very fast to do your compilation. So in order to get to do all of those things, it's not just writing a compiler, it's also how you design the compiler. And that's where Rust really comes in. It's really good with all the usual features that you've heard of so far. So without, now that I've talked so much about it, I also want to sort of spend some time on, what happens in a typical compiler, at least as it relates to Cranelift. This is the same thing that happens in pretty much every compiler, except that, you can have multiple layers of abstraction. In Cranelift, you take what is called your source code, let's say a Rust source code, and it needs to get converted into what is called Cranelift intermediate format. It's called cliff. All right, and then the red box that you saw from earlier, that's the optimizer. All right, that's why we do some optimizations with that on that cliff, and then everything after that is your backend. We do things like register allocation, all that. That's all compiler talk. It's not very relevant for the Rust piece, but effectively speaking, all of this is fully written in Rust, and because of that, the most important thing that you can see is at the bottom. All right. The faster compilation point that I talked about is possible because a lot of the Rust features that we really like are helping over here. Macros, for instance. Cargo's build system itself, or rather Rust's build system, which uses Cargo, is heavily used to basically create a lot of files that you don't want to handwrite in Cranelift. And then there's a lot of well thought out abstractions, the one that I just mentioned, so that you can really make compilation faster. They're called things like dens, entity references, etc. These are things where if you wanted to implement a hash map, you generally have to actually go ahead and say, I have a key and I have a value, right? That's the bare minimum that you'd want to do. But in Cranelift, the hash map is actually implemented nothing but a vector. You're not even using the key actually at runtime. It gets compiled away. So abstractions like this really help you create very well thought out design that can really scale wherever you're, for any kind of project, not just the compiler project. So that's this is just an overview of the Cranelift code gen pipeline, since we've been talking about it so much, and also to get a feel for what it is, what it means to use Rust when writing a compiler. So that's the code gen pipeline. But now let me get to the last part, which is where I would say maybe some of you may be interested in sort of diving into it and understanding why this makes more sense for you, or why you should be interested in this. So there's a lot of stuff happening in the automotive world, and since we're in Bosch, we're talking about automotive use cases. HPC is basically an abbreviation for high performance computing. It can mean a lot of things. To the AI world, it means basically running your AI workload on the GPUs. For us at Bosch, an automotive company, we talk about ADAS, which is Advanced Driver Assistance Systems. We talk about things like battery algorithm management. We talk about things like simulations for large-scale simulations that you want to do in respect to automotive, functionality. All of this stuff falls into the HPC category. This is a new computing paradigm because you are not just reliant on, you're not just going to be running your compute on your CPUs. You're going to be moving out of your CPUs, which means you're going to use an accelerator to do this kind of work. The CPU is no longer enough. And then software-defined vehicles is again an abbreviation. It's called SDV, where the goal is you want to extend functionality of your automobile, or you want to basically go ahead and improve existing functionality. Right? You want to either do one of those two things after the fact. That means after you've made the sale, the car is in the field. You want to provide a better experience for your car. It can be something as simple as increasing your car's BHP by 30 BHP. Everybody like that, right? If I can get 30 more horses on my car, I can make it go faster. I can feel the exhilarating power, all that stuff. It's actually happened. I don't know if you've read some news articles, but Tesla rolled out an update And all that's possible because of some level of software-defined vehicles. What we're trying to say is, you're trying to decouple the hardware from the upper layers so that it's easier to, write applications that can exploit the automobile itself. So, and a lot of other use cases over here. A lot of computers moving to the edge. That means you don't want. We've talked about. Balaji mentioned us talking about voice being a very important user interface. That's pretty much the user interface in many scenarios is what we're talking about. In order to get something like that done, you don't want to send your voice to the car and wait like a couple of minutes before you get a response back. So the compute needs to happen on the car, inside the car, that is. So this compute moving in over there, again, I'm not specifically talking about CPUs, I'm also talking about other kinds of processors. And the key thing that we are observing is that there are two fundamental shifts that are happening, which is RISC-V is, anybody knows RISC-V? Yeah. So RISC-V is another architecture. It's an open source ISA standard, and there's a lot of momentum in this direction, along with Rust, as you can see. We think that all these pieces put together, we're heading into a scenario where there's multiple technologies that are sort of swirling and merging in, etc. And to exploit all of these curves of intersection, we certainly need to know, how to write software for this kind of domain or this kind of world. And that's where compilers are really going to come in, is something, it's at least my thought, all right? I can give you examples of some things that we've been exploring. For example, we want to ensure that there's a certain level of assurance that you can provide for compute that's running on your vehicle, right? You want it sandboxed, you want a trusted execution environment, etc. Now, you can do this on in your regular computers because this technology already exists, but how do you do this on your constrained devices or embedded devices? That's a situation that we need to get to. So basically, you're going to have to talk to your processor and its particular instruction set that it offers to help you secure your whatever compute you want to run, whatever workload you want to run. Another example can be you've got a lot of crypto computing that you want to do. You got some encryption, signatures, hashing, or some zero-knowledge proofs that you want to compute, whatever it is that you want to do. This stuff is not happening on the CPU because that's it's going to take up CPU time. You want to offload it onto a coprocessor. Well, how do you work with a coprocessor? You need to know what the coprocessor does. So again, you'll have to reach into the compiler for this. Same thing goes for domain-specific optimization. I've already written the application. It works, it runs, it's great. But I've got this new requirement for my customer where I need more performance to achieve that objective, which means I need to operate at the same budget, that's power budget or performance budget, etc. But I need to squeeze out more. How am I going to do this? You saw that red box in my first slide, the optimizer. You need to go and tweak something in there and figure out whether you can pull out more performance in your code. All right. And then I talked about things like new targets. We have RISC-V coming in the picture. Obviously, RISC-V has always had support for the major compilers like LLVM and GCC. But what if you don't want to use them because you're going to be bottlenecked by LLVM and GCC, right? We have scenarios where we have proprietary processors that I can't talk about, and we have some open source stuff that does not have support for we don't have compiler support for it. How are we going to support them? The compiler can really back us up over here. A use case can also be something like this. We want WASM or WebAssembly running on bare metal devices where there's no operating system. Can we do that? Right? There are some scenarios that we've explored. That would really make things simple for us. It basically means the same code that I run in the cloud, on the edge, where operating systems are present, I can run it on my device, where there's no operating system. But I can expect that the safety, the performance, and the reliability of that code remains constant. That's a huge ask. If you want to achieve that, we need to start looking at stuff like this. Lastly, this is not yet supported in Cranelift, which is the last part where I mentioned new architectures. Well, GPUs, what's called DSPs are, in other words, very large instruction width architectures, or things like the SIMD part is supported in Cranelift. You guys know what SIMD is, right? Okay, so SIMD is a scenario where it's very much like what GPUs do, but rather in CPUs, if you wanted to issue a single instruction, but have that instruction operate on multiple data elements, because today when you issue an instruction like add two integers, it's going to be a single instruction with two different elements of data. What if I wanted to say that, do the sum on, I don't know, maybe 256 different elements, right? That's basically what SIMD is, where we're saying single instruction, multiple data is what we know. That part is present in Cranelift. And then there's also things like TPUs, NPUs, everything that you have on your phone. All the big keynotes that keep happening saying, we can remove objects from your photos. We can, really profile your voice. We can take away your privacy. All that stuff is happening on the NPU, just so that you know. But all these use cases, for all these use cases to be possible, you need to be touching the compiler in some form or way. And it's my belief, at least, that Cranelift is a very, very good project that can help us do that. Specifically for the fact that, of all the things that I mentioned, and also because of the fact that as we're a Rust community, because of the Rust, the entire Rust ecosystem that comes together for that project, right? Yeah, so that's just my 20 minutes. I guess I'm in 20 minutes or over, I'm not sure. But that's about it. So you can follow me on any of these places. Anyway, we'll be sharing the slides with you as well. And the other point I'd like to mention again is if you're interested in something like this and if you want to really talk about something like this, there are more in-depth streams that we do and that we've already recorded and stuff. It's available on YouTube. You can look me up over there. Okay. Yeah, that's it. And if there are any questions, I can take it now or take it there.
No, we'll have one more talk.
A question, is there
One question is there?
someone raised
One question.
Is there any?
one more.
Is there an LLM-based solutions already there in the company? Because at least since it's brand new to the market.
What?
All the displays that the previous
No, hands down.
Yeah, so LLM-based solutions on the compiler there are some papers that I've read, but nothing practical and production ready as such. There's work because right now what they're really struggling with at least from what I understand, is the reasoning part. LLMs are very good at a specific job, which is they're able to understand patterns and very, very complex patterns and maybe predict what the next pattern is going to be. But this stuff actually requires quite a bit of reasoning.
maybe I put it the other way. I use Kubernetes.
Ask
So,
tell to
for me, it's impossible to write the R library, rewrite the configuration without Kubernetes. I go to a timer, select the prescaler, the values, clock, one prescaler, what say I want to copy the button, I get the code. Now, I still feel this is a bit old fashioned compared to the LLM library. Imagine there is a window on the top where I type it.
Exactly
I
what
speed of them, deadband of 20 microseconds.
I told him to
Triggered by timer 6. If I type it, when these values are configured on its own, it's enough. I can manually check it, then I push the button. Now I have to really go and click everything manually, which can be avoided with LLM.
I think that makes sense because that's you don't really need a compiler for that. That's mostly source code generation. And
It's not a compiler, so that's
yeah.
source code.
Yeah, so that's certainly possible. The additional piece is there is a, to add to that, there is some research around leveraging LLMs for optimization. And that's the part what I was talking about where reasoning is required. But to your point, configuration saying, I want this configuration, just going to type it in English. You help me put the configuration together. I guess that's a very good use case.
Now, if I take CubeMX, which is a native application of ST, and they generate the code in C, imagine I want to do it in Rust. Who should I approach? The community will take care, or ST guys should do it.
Yeah. So one is the configurator is built by ST, CubeMX. I don't think it's open source, right?
It's not open.
Yeah. So, well, LLMs are based on data. So, if we have enough information to say that we were able to train that to look for, or to be able to say that, okay, you can speak to it or you can type it out and then you should be able to produce a configuration. That, but I presume STM, I don't think we'll be able to do it without STM. That's all. So we probably need STM, and I'm assuming STM should have thought of this use case for that, as part of the IDE extension.
We can select C, C++, Rust.
Yeah, that's it. Yeah.
Yeah, my question is about evaluation between RISC-V and Cranelift actually. About
Oh yeah, so you got very sharp eyes. Thank you very much. So RustC is the front end. Alright, so RustC is where we do things like type checking and borrow checking and even our MIR, Rust's mid-level intermediate representation, and some level of optimization is done with that. That's what RustC does. RustC is already written in Rust, the front end. Cranelift is at the back end. That means it includes the mid end and the back end. So data and back end. Cranelift takes care of the mid end and the back end, where whatever RustC produces, it has to produce Cranelift IR, or it produces LLVM IR. If it produces LLVM IR, the LLVM code generator kicks in. If it produces Cranelift IR, then you can have the Cranelift code generator. You can then produce the code. Yeah. Right? Yeah, I hope this is useful. Compilers are always like this. So, if you're very interested in something like this, please feel free to reach out to me. Thank you.